Like, I wa- okay. I assume people will do it on their own. Hello, people. It is nice to see other humans. Um, okay. Yeah, I'll just start. Mm, share. Hopefully I'm sharing the right tab. Yeah. Ananda would be very scared right now if he's sharing his WhatsApp. Okay, so that's a random joke. Um, hopefully this works. Let me try writing some. Okay, that works. Um, so let's start somewhere. Basically, today's class will be about quadratic residues, QRs. Um, there are three topics actually, which I think are kind of connected. The thickness is way too high. Okay. Pell, QR, and Vieta jumping. Can anyone tell me what they think is the I mean, it's completely okay if you've not heard of these, but if you have, what do you think is the similarity?
Like all
If
related to quadratic congruences.
Yes. So these are three things that come into use a lot when you have like equations which have quadratic stuff. So let's say you have to solve something like x squared plus 2x plus y equal y square or something of this sort. Um, all three of these are pretty much related directly towards quadratic equations in the sense that QRs literally has quadratic in his name. Vieta jumping is all about finding the other root of a quadratic equation, and Pell's is literally the solution to a quadratic sort of thing as well. Um, so, these are three things that come up a lot when you have these sorts of equations. And obviously, I'm not covering all of them. I'm mostly just covering QRs today. But the point I'm trying to raise is that the biggest use of this usually in Olympiads is when you have some sort of equation which is of degree 2 and you want to solve it. Um, but before we start solving equations, we really need to figure out what exactly do we mean here. So the basic point of QRs is you just go mod a prime and you check if your number x can be represented as some other number squared, mod p. So if this is possible, then x is called a QR, and if it's not possible, um, then it's called an NQR, so a non-quadratic residue. Um, so for example, 1 will be a quadratic residue because 1 is 1 squared. Um, and 4 will always be a quadratic residue as well because 4 is always 2 squared. But something like 2 may or may not be a quadratic residue based on your prime. So let's say we're working mod um 7. Is 2 a quadratic residue? That's the question.
Yeah, it's useful.
Yeah, 2 is 3 squared because 3 squared is 9, which is the same as 2 mod 7. So 2 is indeed a quadratic residue. But if we worked mod 5 instead, then, unless I'm messing something up, I should just be able to say that 2 is not a quadratic residue. So whether you pick 1 here, you'll get 1 square. You pick 2 here, you'll get 4, which is minus 1. 3, you'll get 4 again. 4, you'll get 1 again. So you'll never get 2 here. None of these squares is equal to 2 mod 5. So 2 is an NQR mod 5, but a QR mod 7. So it really comes down to what your prime as well is. You can't just go around saying X is a QR. It has to be X is a QR mod this prime. Unless, of course, X is a square itself, in which case it's always a QR. But yeah. So, but by the way, there was one interesting thing we noted here, which is also kind of intuitive, which is that if you look at 1 square, 2 square, in fact, we'll look mod 7 because we just saw mod 5 already. So let's look mod 7. What are these values? This is 1, this is 4, this is 2, this is also 2, this is 4, and this is 1, mod 7. So any basic observations?
It's going to be symmetric around, like it's
Yeah.
symmetric around n by 2.
Exactly. And that's actually not hard to prove because if you have ever that I square is congruent to j square mod 7 mod p, that means that p divides I square minus j square. So p divides either I minus j or I plus j. But if we assume that I and j are different residues, so like let's say 6 and 1, um, then p definitely doesn't divide their difference. So p must divide their sum. So that is to say that if two things are equal, then they have to be like the opposites. And the contrapositive, the opposite is also true, because if I plus j is divisible by p, then I square minus j square will also be divisible by p. So the point is that you can really think about the first half. And this actually also tells you how many QRs there will be. Because this is saying that whenever you're in the top half, you can never have some sort of collision, because the collisions can only happen when they're either opposite or they're the literal same thing. So that tells you that the number of QRs mod p is exactly p minus 1 over 2. Because, okay, there's a little bit of a question on whether we count 0 as a QR. Um, for now, we'll just think of it as um, neither. So it's neither a QR nor a NQR. It's just 0. Um, but let's get into some interesting questions actually. So this is just meant to highlight an interesting property of QR. So what happens when you multiply two QRs mod P? Um, will you get a QR or an NQR? This one is reasonably easy. Okay, something in
Yeah,
chat.
you'll get a QR.
We will get
Okay.
another QR.
Yeah, because if this is a squared and this is b squared, then you just get ab whole squared, which is some number squared. So yeah, it is a QR. Um, okay. What about QR into NQR?
And QR.
It depends
NQR.
on N.
Um, what is N? No, N is not a number here. Where NQR is a single expression. Like it's a number which cannot be represented as the square of some other number might be. It's not QR into N into QR, if that's what you were confused about.
It will be NQR only.
It will be NQR.
Why so?
Because if it's QR, then we can like move other QR to
Yes.
like this.
So a little
Yeah.
bit of cheating, but because you can do inverses mod p, you can say that if this is a squared and this is b squared, then and this NQR is supposedly also equal to b by a, or maybe I'll just say b inverse squared. Um, and this is some number squared, so it cannot be an NQR, so that's a contradiction. So if this was a QR, then we would have run into a contradiction. So we must have been wrong in our assumption, so this must be an NQR. And the most interesting one, of course, is showing that when you have two NQRs, the product actually happens to be a QR. This one is slightly non-trivial. So how would we show this? There are pretty cool proofs of this. Has anyone seen any of this? Also, okay, for what it's worth, if you have NQR into QR, that's also NQR. I mean, surely, right? Like commutativity of multiplication. Okay, I should say mod B. Hmm. And yeah, assuming that this final result is true, by the way, does anyone see anything this looks like? I mean, does this remind them of some
Positive, yeah.
basic thing? Sorry?
Positive. Multiply two positives to get a
Yeah,
positive.
yeah, 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 exactly. So it's like you can think of your QR being a +1 and your NQR being a -1. And then when you multiply two NQRs, you're doing -1 into -1 equal +1 and so on. So actually, this is exactly what we will do right after. We will define some notation where this starts making sense. But for now, actually, let's think a little bit more about um, why why is this true. So let's So the thing is, when a number is a QR, and this is going to be a common theme through the lecture, um, it's very easy to think of a number that's a QR because you can just say it's literally some number squared. But when you have to say that it's not a QR, that's very vague, right? How do you say that? You can't say it's like a times x squared because then you have to say a is also an NQR, and like it's kind of like self-looping. So the only sort of way of doing things is some roundabout way when you have NQRs. Um, that's an interesting way of thinking about it, yes. So you can use primitive roots to solve this. Um, I'll s- I'll talk about that as well, but before that, I think I'll start with something more elementary. Um, oh God. Okay, I just got some interesting call. You guys can still see my OneNote, right?
Yes.
Okay, cool.
Yes.
Um, so let's actually fix an NQR. So let's imagine some number like A is an NQR, and let's try to see what happens when we multiply it with each of the numbers from 1 to p minus 1. Now this set is equal to A, 2A, 3A, p minus 1 times A, which actually happens to be the original set in itself because these are p minus 1 numbers, and if any two of them were equal, so if IA was equal to JA, then because A is non-zero, we can cut off the A. And okay, I mean, cutoff is not the most formal thing, but I mean, you get what I mean. So I would have to be equal to J, which we can assume is not true. So basically, any two different numbers here will be different mod P. And because they're exactly P minus 1 of them, this should be 1, 2, 3 till P minus 1. But the point I'm trying to raise is that when you multiply this NQR with the P minus 1 by 2 QRs, then they should lead to P minus 1 by 2 NQRs from this because NQR into QR is NQR. So you can think of this 1 to P minus 1 as P minus 1 by 2 QRs and P minus 1 by 2 NQRs. So the point is that this leads to P minus 1 by 2 NQRs, and then you're left with these numbers. But like the final set is supposed to have exactly P minus 1 by 2 NQRs. So everything else that we have not actually evaluated so far must be a QR. That I did not put that very well, but I hope that makes some sort of sense. Basically, if you're multiplying an NQR with the union of two sets, one is P minus 1 by 2 QRs, and then the other thing is P minus 1 by 2 NQRs. And you know what's going to happen here. So this is going to lead to P minus 1 by 2 NQRs. So, but because they're exactly P minus 1 by 2 NQRs, everything else must be a QR. Oh, that was not in the denominator. Um, so the point is this into this should always be a QR. So NQR into NQR is always QR. A much more general way of thinking about this though is to think in terms of primitive roots. I'm not sure if everyone here has knows primitive roots, but I'll just say it. If it doesn't make sense to you, it's okay. Basically, in general mod a prime, there'll always be a primitive root g, such that if you take g squared, g cubed, all the way till g to the p minus 1, these are all distinct numbers and cover all the p minus 1 different residues, which are non-zero. And it turns out that the QRs are now exactly the ones where the exponents are even, which makes sense because I mean, if the exponent is even, so if you have something like g to the 4, then this is definitely g squared the whole squared. But because that already covers p minus 1 by 2 different QRs, everything else must be an NQR. So again, we're kind of using the same sort of trick. And these are all QRs. And then it's pretty clean, right? Because now you can think of your NQR as g to the odd. And then you're just saying g to the odd into g to the odd is g to the even, which is true. So that's another way of thinking about it. Does anyone have any questions about what I did so far? Also, like, feel free to stop me at any point if what I'm saying doesn't make sense to you. Um, but now let's actually get past this sort of, um, like, these are sort of just properties, but okay, what do we really care about any of this? It really gets interesting when you define this notation, which is saying that A by P is +1 if A is a QR, mod P. P is a prime. That's important because there's actually this notation is actually defined when P is not a prime as well. But then this is not really true anymore. But we'll see how that's happening. And it's equal to -1 if A is an NQR. And then the cool property that ends up being true is that A by B times B by P is AB by P, which is literally what we just proved. Like if you have QR and QR, it goes to QR. If you have QR and NQR, it goes to NQR, etc. So basically, if you want to evaluate something like 6, whether 6 is a QR mod 7, it's equivalent to check whether each of 2 and 3 are QR mod 7. And really, when things become magical is when we announce this big thing called quadratic reciprocity. And what this is that if you, okay, the actual theorem is for just odd numbers, but ideally you should only be using it when m and n are primes. But I'll just tell you how it works in general. This says that this is true. So, m by n into n by m this is true when m and n are odd. It's worth understanding what happens when p is not a prime. So the definition actually is that a by pq is just a by p times a by q. And why I don't really like using this is because if you want something like 2 by 15, this is equal to 2 by 3 into 2 by 5. And because this is an NQR mod, each of them, this is -1 and this is -1. So 2 by 15 is +1. But that definitely doesn't mean that you can achieve the residue 2 mod 15 because you can't achieve it mod 3 itself and you can't achieve it mod 5 either. So surely you can't achieve it mod 15. So the definition of it being whether 2 is a QR mod 15, so 2 is some squared mod 15, that whole thing fails here. So it's kind of suspicious when you start using it like this, but sometimes it's okay to do that. Like it depends on whether you really care about it being a QR or not. Um, so the point is, if you ever have something like um, if you ever have something like 3 by 10, you can not 3 by 10, it has to be odd. 3 by 7. No, 7 is a prime. 77. You can just multiply this by 77 by 3. That's legal, but um I would prefer not doing this. In fact, you never usually get to the point where you need to do this. Usually, the point where you could be doing this is you have 77 by 3 and then you do 3 by 77. This, I think, is not a great idea. Instead, what you should probably do is split the 77 into 7 by 3 and 11 by 3, and then multiply by 3 by 11 and 7 by 3 by 7. I mean, this is just for the sake of, I don't know, being safe. There's no real reason to do this.
I have a
Okay.
question.
Yeah, go ahead.
So, like, wasn't the point of this notation to check whether a number was a quadratic residue mod P or not? So
Yeah, so that's
then,
true when it's a prime. But when
okay,
you
okay.
do it for general things, they just defined it so that it extends nicely with this
Okay.
definition.
So when you have a like composite, you can split it into its prime factors and then do the same thing.
Yes, but you have to be careful in the sense that when the denominator is composite, it may not anymore represent whether the number itself was a QR or not. It's just some definition.
So it's just for extension's sake. It's not
Yeah,
actually
yeah,
okay.
exactly. Which is why it's avoidable as long as you can avoid it. Like try not to make your denominator a composite. Um, Anyway, actually, before we got to this, maybe something I should have spoken about is what is minus 1 over p? So basically, when is x square plus 1 congruent to 0 mod p? When does this have solutions? Has anyone seen anything of this sort before?
P equals 2, or we are talking about operator.
P equal to, in general, we will ignore through this lecture.
P is
Uh,
1 mod 4.
P is 1 mod 4. Um, P is 2 is also correct though, so I won't say that's wrong or anything because you can choose x equal 1. But I'm mostly looking at odd primes. And there's a Fermat's Christmas theorem, I think, which says that this solution has equations if and only if P is of the form 4k plus 1. And the proof, which usually goes, is something like you have x squared is minus 1, so x to the 4 is plus 1 mod p. But then you try to guess what the order of x was, and it could not have been 2 because literally it could not have been 2. It could not have been 1 either because if x was congruent to 1, then x squared would have been congruent to 1. So the order has to be exactly 4, and then you get something like 4 divides p minus 1. Again, if you have not done orders, then it's okay to just ignore this part of the lecture. But yeah, like you basically get that 4 must divide p minus 1 if this has a solution. So actually, a clean way of saying this is minus 1 to the power p minus 1 over 2. And actually, that turns out to be something you can say in general, because you can say that a by p is a to the power p minus 1 over 2. Because if a was a QR, then a is some number squared, and then you just get t to the p minus 1, and any number to the p minus 1 is 1 mod p by Fermat's little theorem. On the other hand, if it wasn't a QR, um, then you would end up with okay, maybe then I'll have to talk in terms of primitive roots. Like, then you'll have g to the odd to the p minus 1 over 2, um, which will turn out to be something like g to the p minus 1 into k into, no, plus p minus 1 over 2, because you can think of this odd as 2k plus 1. And this becomes 1. So it's just g to the p minus 1 by 2. But this is equal to exactly minus 1, because if it was equal to plus 1, then g to the p minus 1 over 2 and g to the p minus 1 are both 1. But that contradicts what a primitive root should do, because it should give all different things. And it has to be exactly one of them, because if x squared is 1, then x has to be plus minus 1. And x squared here is 1. Okay, so again, these are kind of things that, okay, someone is here. Is that an unmute by mistake, maybe? I'll just mute. If you have a question, you can unmute again. Okay, now that we have spoken of enough nonsense, let's actually do some nice question. There's one last thing, by the way, okay, which I should mention, which is when you have 2 by p, because you can't change this into p by 2. That's not allowed because these have to be odd numbers. So 2 by p has its own formula. I mean, one thing you could do is say 2 to the p minus 1 over 2, but it's not easy to evaluate. What you can say is, correct me if I'm wrong here, I think it's this. And the proof of this is actually pretty cool. You can Google it up. The proof is actually like you take some sort of permutation and you do some sort of manipulation on it. And it works out pretty cleanly. But I won't really get into it. Okay. Let's actually do a problem, because I feel like we've spent enough time without doing a single problem. So let's say 10 divides x square plus xy plus y square. And we'll prove that this actually implies that 100 divides x square plus xy plus y square. Okay. So think about this for like a minute or two, and then we can talk about what's going on. Okay, does anyone have any ideas? Go ahead, Mathur.
We consider mod 2 and mod 5 separately. Since
Yeah, that's very true. So surely 5 dividing the expression should not impact whether 4 divides the expression. So really the question is saying that if 2 divides x square plus xy plus y square, then 4 divides it. And if 5 divides it, then 25 divides it.
And from here, find a better thing than just grinding.
Sorry?
And from here, I couldn't find something better than grinding with case one.
Yeah, so for 2, it's not even bad, right? 2, there are like 4 cases on x and y. So if x and y are like both,
Why equal modulo 2, then the conclusion is not hard to see. Then
yeah, I mean we'll just do all 4 cases, right? If it's 0 comma 1, then you just get 1. If it's 1 comma 0, you get 1. If it's 1 1, then you get 1. And if it's 0 0, you get 0. This is x and y, and this is the expression mod 2. Um, so the point is that x and y both have to be 0 mod 2 for 2 to divide this expression. But if x and y are both 0 mod 2, then 4 divides each of these terms. So 4 divides this. That makes sense? Yeah, someone raised their hand. Go ahead.
We could also do the same thing for 5, and then but for x square plus xy plus y square, it would be, if it's congruent to 0 mod 5, then x plus y square must be congruent to xy mod 5 too.
Sorry, go ahead, repeat.
Since x plus y square is x square,
Mm-hmm.
x plus y whole square is x square plus xy plus y square.
That's 2xy plus y square.
Yeah,
So
two
you'll
x
have to do something like this.
Right. So this would be congruent to 0.
Uh-huh.
So then we have only a limited option for xy mod 5.
Yes. So that's the point here, that if you want, you can bash this out, and probably that may even have been the intended solution. I have no idea. But actually, I could.
For 5, there is another solution. I mean, without bash,
Okay.
without quadratic residues, I
Okay.
could not
What's
think.
that?
So we can just take x by y, matlab
Mm-hmm.
x y inverse mod 5 as a. So
Yeah.
a square plus a plus 1 is 0 mod 5. So a cube minus 1 is 0 mod 5. Means inverse of a is 1 mod 5 if a is not 0, means 5 does not divide x or y.
Huh?
So a has to be 1 mod 5, which clearly doesn't work, so a has to be 0 mod 5. So 5 divides x or y, and if 5 divides one of x or y, then it divides both. That can be easily seen.
Okay. So yeah, this idea is also pretty cool. So if you have is, you can think of it like this: assuming y is not 0. That's the first assumption here, mod 5. So if that's true, then if y was 0, then x square would be 0. So x is also 0, so that's fine. Um, and if not, then you have a square plus a plus 1 is 0 mod 5. But then you multiply by a minus 1, and then you get uh, either a was 1 mod 5, which is to say that x and y are the same, but then 1 plus 1 plus 1 would not be 0 mod 5, so that's false. So a cube has to be 1 mod 5, but then a cube is only 1 mod 5 when a is a is 1, right? Surely. Uh, yeah. So this should imply that a is 1. But that fails. So this whole method has to be wrong because y was indeed 0, which implies that x also was 0. So that is one thing that works. Now I'm going to change the question slightly, and I'm going to put an 11 here, and I'm going to put a 1 2 1 here. So actually, the same thing we did with 2 and 5 also works for 11. It also works for 23. So um that's kind of the problem for you guys. Like you're going to run out of tricks, whereas QRs is not really going to run out of tricks. Although a method similar to this, I still imagine is not impossible, because you can still say mod 11 something like this is true, and then the only question is, how do you check whether a cube congruent to 1 mod 11 has solutions or not? That's the part that will get slightly weird.
You can do it
Um,
orders, right? I mean,
oh yeah, you can just use orders. You're right.
also
Yeah,
like
that's true.
I think I have a solution using quadratic residues.
Mm-hmm. So yeah, actually, this solution actually works in general then, yeah, because the condition on the numbers here is that they all need to be of the form 3k plus 2. So 2, 5, 11 are all 3k plus 2, and then in that turn you would get a cube congruent to 1 mod that number. So 3 would should divide 3k plus 1, but that's false. Um, so yes, the solution actually does work. But yeah, let's now look at the QR thing. Go ahead.
Yeah, so in case whatever earlier question was 5, so in this case I guess 11.
Mm-hmm.
So if 11 divides x square plus xy plus y square,
Mm-hmm.
and we assume that 11 does not divide either of x and y, because
Yeah.
if it divides either one, it divides the other two.
Yeah.
So then you can just multiply the equation by 4 because you want to somehow create perfect squares.
Yeah. Perfect.
And then you just get what 2x plus y whole square is congruent to minus 3y square.
Yes. So this is kind of a trick here, which is, I think someone gave a very nice idea earlier of x squared plus 2xy plus y squared minus xy. The issue is that you get left with that xy term, and we don't really know how to deal with an xy term. Instead, if we were left out with this a term like 3y square, that's perfectly okay with us because that's also a square. So if you can write this like this, minus 3y square mod 11.
And
Um,
you can just divide by y
hmm.
square and then
Yeah, so you're basically saying that minus 3 is a QR.
which we know is not true.
Yeah, so
If
how
I
do
can
we check when is minus 3 a QR? So let's say minus 3 by p. We'll try to generalize this to general p, see when we can use this trick. So minus 3 by p is supposed to be minus 1 by p times 3 by p. But by our by our quadratic reciprocity trick, this is supposed to be minus 1 by p. Okay, maybe I'll do it separately. So we know that 3 by p into p by 3 is supposed to be minus 1 to the power p minus 1 into 2 by 4. So this is just minus 1 to the power p minus 1 over 2. And the interesting thing is this thingy is also minus 1 to the power p minus 1 by 2. So you can think of this as just minus 1 by p. And then you're saying something like, so this is equal to minus 1, and I'm going to use fractions, which is slightly suspicious, but it's okay, I think. Into p minus 1 by p by p by 3. Does this make sense? Because I basically transfer this here. So 3 by p is minus 1 by p by 3. And this into this is always plus 1. And note that 1 by x is just equal to x when x is plus minus 1. So really what I'm saying is that this is equal to p by 3. So basically, if this was 1 initially, then p must have been a QR mod 3. But the QRs mod 3 are exactly like 1 by 3 is a QR and 2 by 3 is an NQR. So if P was 3K plus 2, then this is false because this is equal to minus 1. So basically, whenever your prime is of the form 3K plus 2, then that would force xy plus y square is 0. Now, I want to mention two things here. One part, of course, is this whole manipulation at the end. That's kind of something you want to get used to. There are also smarter ways you can pull this off. Like you can just because my 1 by x is really the same as x when you're dealing with plus minus 1, you don't really need to do these denominator things. You can kind of skip some of these steps. And because x squared is always 1, you can sort of skip some of these things as well. But I think the more important thing is like this whole trick of multiplying by 4 and getting to this sort of equation. And this is something that comes up a lot. You always want to complete the square and so that you get some sort of expression where you eventually end up with just a singular number being a QR, independent of your x and y. And then you want to just work with that. Because if you have a singular number which is just supposed to be a QR, you can deal with that. But if x and y are in your things, then it's very suspicious. So earlier, for example, if we knew that x plus y whole squared is xy mod p, this is actually saying that xy is a QR, but that's kind of hard to deal with. On the other hand, if we just know that minus 3 is a QR, that's sort of easy to deal with.
1 second.
Mm-hmm.
How do you get like from minus 1 to the power p minus 1 by 2 to minus 1 by p?
That's the definition. Like here we know that a by p is always a to the p minus 1
Okay,
over
so I
2.
just use this.
Yeah,
Okay.
yeah. Because like if a is g to the even, then where g is a primitive root, then you just get g to the p minus 1, which is just 1. And if it's g to the odd, then you have to get to minus 1. So it's just something that works out. Or you can also just notice that by Fermat's Christmas theorem, this is true. But that's not really the big deal here. It's also pretty lucky actually that this minus 1 by p, exactly cancels out with this minus 1 by p. So that's pretty neat. Okay. Let's look at another problem. Give me a minute. Okay. So prove that for okay. You want to find all solutions to 2013 times xy plus yz plus zx divides xy plus y square plus z square. And x, y, z are positive integers. And this is a 2013 contest problem, so obviously you can imagine that 2013 is not very relevant, but it can't be totally irrelevant either.
Is 2030 a prime?
Sorry?
2030 is the prime?
Notice that it is divisible by 3.
Ah, right.
Okay. Actually, in fact, we won't even bother factorizing further. I'll give you guys a hint. All you need is the factor of 3. This is all
Yeah,
you need.
that's why like into general.
Yeah. No, but this is actually kind of difficult to guess because if you actually factorize the entire thing, you get 11 and 61 as well. And then you feel like maybe you have to use 11 and 61, but it turns out all that matters is 3. I hope. Yeah, I think so. I don't really remember for sure. So actually, I'll just say 3, right? If I'm claiming that only 3 matters, I can just say 3.
Pretty
So, I mean,
unlucky
I'm not really
because
starting. Sorry, go ahead.
pretty unlucky because if it were 2, then we would get a perfect square directly by adding.
If it were 2, then yes. But why is that really unlucky? I think we're going to do that either way. So actually we'll rewrite this a little. We're going to say x square plus y square plus z square is 3k times xy plus yz plus zx, or some k, just by the fact of this divisor. And then we'll add 2xy plus yz plus zx. So I'll just skip the step and I'll say x plus y plus z whole square is 3k plus 2 times xy plus yz plus zx. So this is just a little bit of manipulation. As much as you can perfect squares, you should when you want to use QRs. So this is something you just want to do. If you think you're unlucky, get past it. You're not that unlucky.
Also, why did you put it equal?
Um, I mean, I chose k so that it becomes equal. Like x
Right.
square plus y square is 3 times, like this times some k, right? Like the only way to do your completing the square is to have equality, because I need to add exactly 2xy plus yz.
Just wondering, in your previous proof, like I
Mhm.
think in the step there, you got like p by 3 in the denominator and then you moved it to the numerator. Like,
Because minus 1 by minus 1 is the same as minus 1 by 1 is the same as 1. Like 1 by x is
okay,
always equal to x when x is plus minus 1.
okay.
But equal. Not even common. Not always true, guys. But yeah. Yeah, that's the point, right? When you have plus and minus ones, your manipulation becomes really simplified in a lot of different ways. So that's pretty useful. So when in doubt, we must take primes. So let's say p divides x plus y plus z. Then we get that p divides this product. And for a moment, let's assume that p divides xy plus yz plus zx actually. Like p doesn't divide 3k plus 2. What does this tell us? Like, okay, you can think of z as minus x minus y here. So you can think of it as xy plus x plus y times minus x minus y. So you get something like, oh, you get something familiar. So from our previous problem, if you can make p of the form 3k plus 2, this would imply that x and y are both 0. and in turn z is also 0. So x plus y plus z, so everything here is divisible by p, and then you can kind of like divide by p out, right? Because you can say then x by p plus y by p plus z by p whole square is this by p square, this by p square, this by p square. This would also be true. Yeah, go on, Raghav.
Yeah, so essentially 3k plus 2 divides x plus y plus z the whole square, which means
Yeah.
there is a prime p which divides 3k plus 2 of the form
Mhm.
2 mod 3,
Yeah.
which was like odd, has an odd exponent.
Yeah,
And
perfect. So, like, the point is that if every prime of which was dividing 3k plus 2 was congruent to 1 mod 3, then, I mean, you're multiplying things like 3a plus 1 into 3b plus 1. So the product has to be some 3 times something plus 1, but we know that it's plus 2. So there has to be something here which is 3c plus 2. And in fact, it must be to an odd exponent, because if it was even, then we could just write it as 3c dash plus 1, because it'll become like 9c square plus this thing plus 4 should be like plus 1. So what Raghav is saying is that there must be some prime factor p here which goes to an odd exponent and it's congruent to 2 mod 3. And then we just use that prime literally, because that prime must divide the LHS, so it must divide x plus y plus z. But then from this trick we get that all of x, y, z must be 0 mod p, so we can divide throughout by p. And okay, we use that it's odd because the LHS is divisible by p to the even, which means that xy plus yz plus zx must also be divisible by p. It's not possible for 3k plus 2 to cover all those prime factor exponents. Okay, I rushed through this a little bit, so if people have questions, like, feel free to like think about this for 2 minutes. I won't move on. But
Sorry,
the
how
main
do you get xy plus x plus y times x minus y? Like did you consider x?
I assume that p is x plus y divides x plus y plus z, so z is minus x minus y. So you can take these two common and you can say x plus y minus x minus. So the main trick I think is noticing that, you know, if p divides all of x, y, z, you can repeat this. So all you need to do is really find some prime which is 2 mod 3, which divides this and this, because then you would be done. And the fact that you can do that is pretty clean just because of this term.
Wait, after you find the prime, like I didn't get the finish.
So after you find the prime, because it's divisible by p to the odd here, first of all, p must divide x plus y plus z because it divides the RHS, so it should divide the LHS.
Yes.
And then p to the even divides the LHS, in fact. And because only p to the odd divides the LHS, there must be a prime factor of this as well in this term. So basically what I'm saying is that there exists a p of the form 2 mod 3, which divides x plus y plus z and also divides xy plus yz plus zx. Is that reasonable? Because if it doesn't divide this, then that means all the prime factor exponents are coming from here, but then they should match. Like here it's odd and here it's even, it's not matching.
Okay.
So, and if p divides both of these things, then p would actually have to divide each of x, y, and z, is what we would get. But then you can divide each of x, y, z by p, and you can do a infinite descent. So actually the only solution is like 0, 0, 0, but okay, we were in natural numbers, so actually there are no solutions. Yeah. So again, the QR part of this is not that big, especially because we've seen that exact expression before. But yeah, this is actually an expression that comes up a fair bit with QRs. And it's pretty neat that xy plus yz plus zx is just a hidden way of saying this if x plus y plus z is 0. Um, okay. Let's do one or two more problems. Hmm. Okay, let me look for the gold collection of problems. Okay, I'll do that after this problem. I'll just give one. Okay, this problem is also pretty Cute, actually. I'll just take the screenshot. Yeah, this is slightly different from the ones we've done so far. Okay, I'm also just pasting some problems here, which we might end up doing. If you have seen this slash just want to try a different problem, you can try this.
Okay, are these problems anyhow related? The first and second.
No, they're totally independent. I'm just like trying to collect some problems which I have.
No, both had 5k minus 1, so I
Oh, I don't actually even remember, but yeah, I don't expect them to be related. There might be some slight common idea, but I wouldn't vouch for that.
If possible, could you quickly walk through the first solution? I was a bit disconnected at that
Yeah,
time.
yeah, yeah. Are you talking about the x square plus y square plus xy problem divisible by 110?
Yeah, 2 and 500. Like I got the 100 part, but that was basically case bash.
Okay. So yeah, I mean the general idea is whenever you have an equation which is degree 2 and you want to do something, you want to complete the square. So wait, where did it go? Oh, there. So you want to write this thingy. It's instead of 2 and 5, we worked mod 11 because actually it works whenever p is of the form 3k plus 2. So if x plus y, xy plus y square is 0 mod 11, you can multiply by 4 so that you can write this in like a 2x plus y whole square. Actually, you can do it directly here. You can say x plus y by 2 whole squared plus 3 over 4y squared. But I mean, just for the sake of avoiding fractions. You can write it like this. So you can say 2x plus y whole squared is minus 3y squared. So minus 3 must be a QR. But that actually turns out to be false just with some manipulation because minus 3 by p is minus 1 by p times 3 by p, but 3 by p times p by 3 we can evaluate. And then it turns out that for this to work, you must have that p by 3 is 1, but that's false when p is of the form 3.
Oh,
Okay. Yeah, it is true that both of these have a thing. Okay, I don't even remember the solution entirely to either of them. We'll figure them out. Okay. Hmm.
wait, what was the assumption in that question? Like we got a contradiction, but what was that?
Oh, the assumption was that we can take this y over here, which is false because y must
Okay,
be
okay,
0.
so that only.
Yeah. Okay. Does anyone have any starting ideas? Okay, what is phi of x? That's a good starting point, I guess. Can anyone define phi of x for me?
prime numbers. No, what I'm telling. Relatively prime numbers of 5 to the m minus 1 before 5 to the m minus 1.
Okay, that is a definition. I do agree, but I was more just looking for just this.
I think it's product of 1 minus 1 over pi for each bracket.
Yeah. Sure. So let's actually assume GCD is 1. Does that tell you anything about phi to the m minus 1 and phi to the n minus 1's GCD?
5 to the GCD of mn minus 1.
Okay, that's actually a very nice thing. And this is something that turns out to be true in general. The proof of this is just uh like I mean you can subtract 5 to the n from here, so you get something like 5 to the m minus 5 to the n, which you can rewrite as 5 to the m minus n minus 1 times 5 to the n. But 5 to the n is co-prime to 5 to the n minus 1, so you can drop this factor. And then basically you do Euclid's algorithm on these exponents. Like you went from mn to m minus n comma n, and you can keep repeating this until you end up with GCD of m. Okay, I guess that was my mistake. And the point is if GCD is 1, then because we're assuming that, then the GCD of these two things should be 4. And that is to say that the number inside and this product should not have a lot of common factors. Should just have 4 as a common factor. So can anyone tell me what they expect as to these exponents?
The product pi to the power of alpha minus 1, that should divide 4.
Yeah. So that's a very good point, because pi to the alpha I minus 1 is surely going to share some factors with pi to the alpha I, unless this alpha I was mostly just equal to 1. So whenever it's not 1, that should be the thing contributing to the 4. Actually, I'll just move this problem to the right. Why am I so bad at this? Okay. So basically, actually, it's saying that the GCD of these two things is at least p1 to the alpha 1 minus 1 into p to the alpha 1. In fact, the GCD divides this. So, but the GCD is equal to 4. So basically, at best, 2 can have a higher exponent, but all other primes should be just a single exponent.
Like, can't you, like, you have GCD equals 4, so can't the only prime factor be 2?
GCD of 5 to the m minus 1 and 5 to the n minus 1 is 4, but this number itself is 5 to the m minus 1. So why should the only prime factor? I'm saying like 5 to the m minus 1 and 5 to the n minus 1 should not have other prime factors, but that doesn't prevent it from having other prime factors. But 2 can have some weird power. But actually we can figure that out. So basically what we've got is 5 to the m minus 1 has to be of this form. Does that make sense? Because if you had square here, then p2 would divide 5 to the n minus 1 as well. But that's a contradiction.
So could you just explain why it's a contradiction again? I missed that.
Because the GCD of these would be divisible by p2. But if p2 is an odd prime, then it doesn't divide 4. The GCD is supposed to.
Okay, got it. Yeah, makes sense.
Yeah. So basically, it has to look exactly like this. And then now that we have this, what does the phi of 5 to the m minus 1 look like? It looks like 2 to the k minus 1 into p2 minus 1 into p3 minus 1. Blah, 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 blah. And one question is, can phi to the m minus 1 equal to the k itself? But if not, there'll be at least one other prime, and that will contribute at least one extra factor of 2. So the point is the GCD of these things will be at least 2 to the k, because 2 to the k divides the first thing, and 2 to the k also divides the second thing, as long as there's at least one other prime factor.
Means 5 to the m minus 1 can't be because of Mihaly-Lesky's theorem.
Yeah. I was hoping we don't need to use that, but I actually am
And
not sure.
then k has to be bounded by 3. So you can bound a number of extra prime factors, because if there are too many of them, then there'll be a high power of 2.
Yeah, so if k has to be bounded by k has to be exactly 2 actually, right? I mean, if k is 3, then and there is no other prime factor, and sorry, and there is another prime factor, then their GCD is at least 8, which is bad. And if it's exactly 2, then the GCD can be at most 2, because there's only one factor of 2 here. So it has to be exactly 2 square. In fact, that's also obvious because 5 to the m minus 1 has to be divisible by 4. So that so you have to have at least 2 square here. So you get 2 over here. And okay, I mean, yeah, there is the case where you have 5 to the m minus 1 equal to the k. There is a theorem which says that if there are powers which differ by exactly 1, then they have to be 9 and 8, which is not the case here. But let's just think if there is a better solution.
Powers, that's like non-zero, you mean, no?
Yeah, I mean, not k to the 1, like perfect powers like k cube, k to the 5, k to the 4.
No, I mean 1 square and 0 square also differ by 1. So I was
Yeah, but
already
okay, positive powers. Yeah, I think someone else also said this
Would you
too.
repeat the part or like why p2 square divides 5 raised to n minus 1 would imply p2 square also divides 5 to the n minus 1?
No, p2 square wouldn't, but p2 would. You would get this, right? Like if p2 square is over here, then you would get p2 into p2
Okay,
minus 1.
yes.
So p2 would be there in the GCD. That's bad. So okay, let's for now take this for granted that this does not have solutions. Um, Actually, it does have solutions because
It is
m equals 1.
Isn't it a conjecture that if powers differ by 1, it's like the 9 and 8?
Yeah, but m equal 1, this is not really an actual power. So we have missed that case. So 5 minus 1 equals
Not a
4.
conjecture, it's called Catalan's conjecture. But
Oh yeah, it's called Catalan conjecture, but it's been proven. It's also Mihalescu's. Um, so it's not a conjecture anymore, guys. Trust me on this. So yeah, I mean there is one case when m equal 1. So in that case, you get phi of 4 equal 2, but then 2 is not of the form phi to the n minus 1. So that's anyway fine. So let's just assume this, guys. I think this much we can do. So let's write this like that. What now?
Guys, we cannot have like more than 2 odd prime, or even like more than 1.
No, you can have, right? You can have lots of them because the GCD will still be only 2 squared here.
No, but like then, oh, okay, okay.
Yeah. Unless there is some weird thing like P3 minus 1 ends up
Yeah.
dividing P2. Those things we'll have to make sure don't happen. So let's start somewhere, right? Let's say phi to the m minus 1 is 0 mod P2. This is true. Is m odd or even? What happens if m is even? We get phi to the 2k. Oh, what did I do? Phi to the 2k minus 1, which is 25 to the k minus 1, which mod 8 is equal to 0 because this is 1 to the k minus 1 mod 8. So the point is if m was even, then this would actually be divisible by 2 cube, which is bad. So m has to be odd. And the reason why it's useful to check these sorts of things is because now we have the very nice sort of constraint that phi to the m plus 1 is 5 mod p2. So 5 is a QR mod P2 because m plus 1 is even. So 5 is a QR. And this is why it's when you're working with QRs, it's useful to just check whether
Why
things
does
are.
QR always show up so unexpectedly?
Yeah, that's a good point. This problem it's definitely very unexpected. I feel like in the other problems, I think degree 2 should already make you think that QR is something I should keep in my head. QR viet appels, that's the way to think about it. This problem in particular, there's no degree 2, so I don't really have that thing on my hands. But yeah, that's something about Olympiads in general, yeah. Like if you knew everything that was coming, it wouldn't be that much fun. So yeah, I mean what we have now is that 5 by pk for each k is 1. And what this is saying by quadratic reciprocity is because 5 by pk into pk by 5 should be minus 1 to the power 5 minus 1 by 4 into pk minus 1. This is just 1, and pk minus 1 is even. So this is minus 1 to the even, which is 1. So this is saying that pk by 5 and 5 by pk are the same thing. So this is equal to pk by 5, which is saying that pk is congruent to plus minus 1 mod 5, because the only QRs mod 5 are plus minus 1. Which is brilliant. Like, I mean, now you're just saying that all of these things are plus minus 1 mod 5. And the reason I call that brilliant is because if any of them was 1 mod 5, then here you would get 0, but this is not divisible by 5. So actually, all of them are exactly minus 1 mod 5, which is like a random brilliant thing we just got.
Just to confirm, the n
Yeah.
n are different, right? Like Pn and I raised to n.
Oh, yeah. I have been reusing variables. Good point. I'll just change that. Yeah, that's probably better. So what we have got is that each of these primes is minus 1 mod 5.
Would
So
be
in turn,
a
each of
number
these
of
things.
those, right?
Hmm?
Would there be an even number of those, since it even number of those primes, since like the LHS is minus 1 and the RHS is minus 1 times a bunch of minus 1s. So you'd even
Exactly. Exactly. So yeah, what you're saying is if you look at this expression mod 5, then the LHS is minus 1. This 2 squared is also minus 1, so we can kind of cancel these things. So basically the product of these has to be 1 mod 5. And because each of them is minus 1 independently, you must have that t minus 1 is even, because okay, these are okay, maybe I'll just say p1 to p1 to pk, where p1 itself is odd. Okay, and then you're saying that t is even. And what does the other equation tell you? It tells you minus 1 is 2 into minus 2 to the power even. So, but that's just minus 1 is 2 into 4 to the power k. But that's impossible because this 4 to the power k is plus minus 1 and this is minus 1. So you're saying 2 is plus minus 1, but that's false. I think I went a bit too fast at the end. Did people kind of catch on to what was going on?
Yeah, it makes sense.
Okay, so the main idea actually is this random trick that 5 is a QR, so you can get these pi mod 5. And this is a very big constraint. If each prime here has to be minus 1 mod 5, that's pretty big. And that's actually telling you exactly what's happening in the bottom thing as well. So that's pretty cool. Yeah, in general, if you have something like so one place where you definitely want to use QRs is when you have squares. I think the other thing worth remembering is that if you ever have a to the b minus 1, it's worth checking whether is 0 mod b. If you ever get to this, it's worth checking whether b is odd or even. If b is even, you kind of get no information, because then you're just saying 1 is a QR, which is just true. But if b was odd, then this actually gives you the information that a to the b plus 1 is a, but then so a has to be a QR. So that gives you some sort of information. In fact, that gives you a lot of information. Some questions on chat. I'll just check. What's the source of this problem? some Taiwan TST. That is indeed true. I'll just tell you the exact source.
And
Yeah,
when
it's
you
some Taiwan
finish
TST.
the problem,
I
that
don't really know
uh,
what Taiwan.
the
Hmm.
power of 2 means -2 to the power t.
Mm-hmm. So yeah, here you get -2 to the power t, but t is even. So it's -2 to the power 2l. So it's become 4 to the power l. So you're saying something like -1 is 2 times -1 to the power l, but that can't happen because you're saying like these two things are +-1, but this is a 2 out of nowhere. Does that make sense?
Yeah.
Okay. So yeah, this is one of the more unexpected applications of QR, I will agree. Like usually you can see QRs coming from a mile away. Like I had a problem on my mocks which was something like x square minus 4 to y square minus 4 minus 12 is z square. X, Y, Z are, I think, positive integers. Like this sort of problem you can see a mile away. Surely there'll be some QRs hidden here. Like, I mean, for starters, you can take a prime factor of x square minus 4, and then you can say z square is minus congruent to minus 12 mod p. So that's saying minus 12 is a QR mod p, and then that gives you some constraints, and then you can do more stuff. And the interesting thing to note though is that this also has a solution with Vieta jumping. So it's very much possible that problems have totally different but both completely correct solutions. And yeah, okay. Um, yeah, actually, this problem is more of a sort of problem where it's not just QRs, you need to do a lot of work around the QR, so people can try this on their own if they want. The step I mentioned is kind of important to see what happens when z square is congruent to minus 12 mod p, but that's kind of just a starting point. And there's also a little bit of messy case bash you have to do at the end to show that some things work out, which I did not enjoy doing in my mock, but it's okay. Yeah, you can just take a mm, screenshot of this or whatever. But okay, let's do this problem.
Why was t even in that case?
That's a good question. It was from the first thing because we had -1 to the power t into -1 is -1. So t has to be even, otherwise you get. I mean, this -1 cancels with this -1, so you should have -1 to the power t is 1. So t is even. Like just looking at this entire equation mod 5. Does that make sense? Like
Yeah.
each of these pi is -1 mod 5. So you have -1 into -1 to -1 t times. Okay, let's try this. So obviously we'll assume a and k are both odd. And okay, I see one thing that is kind of common already, which is that you have that a to the b minus 1 here. Like, so what this is saying is that if we let p divide a to the 4 plus 4,
One thing I'm
then
saying is, Sophie.
yes, that's a very good point as well. A to the 4 plus 4 can be factorized as a square minus 2a plus 2 into a square plus 2a plus 2. And I hope it's this, right? I think it's this. Am I right, guys? This is like a minus one. Wait, how do you do this again?
Yeah,
Oh, it's like a square plus 2 whole square minus 2a whole squared. Yeah.
that
Yeah,
sounds
it's correct.
Yeah, okay. Yeah, and we will use that factorization at some point possibly. But for now, let's actually just think about p dividing this. So p divides 5 to the k minus 1, but k is odd because we've assumed that. So 5 to the k is congruent to 1 mod p. So 5 to the even is congruent to 5 mod p. So that actually implies that p is plus minus 1 mod 5. from our previous example, by the way. So there is some
Key
overlap.
even?
You have that again.
Why is
PT
key even?
Sorry,
Why is key even?
k is odd. So 5 is when I multiply both sides by 5.
Oh,
Like we assume that either a or k is even, we'll assume a and k are both odd, and we'll prove that there's a contradiction. Does that make sense?
yeah, I got it now.
Okay, so basically, if p divides a to the 4 plus 4, then p must be plus minus 1 mod 5, which is pretty crazy. And also, for example, 5 cannot divide a to the 4 plus 4, because then 5 doesn't divide this.
So we can use the factorization now, or
We could do that, but even simpler. Wait, I don't actually know if it's even simple. Okay, it's kind of okay. You have to do some
We can
factorization.
use the,
But
I think
yeah,
factorization gives it here.
yeah, but okay, even before that, actually, you should note that a to the 4 mod 5 is always 1 or 0 mod 5.
Yeah, by far now.
Yeah, so basically, if a to the 4 was 1 mod 5, then the LHS is divisible by 5. But that shouldn't happen because 5 doesn't divide this. So actually, a should be 0 mod 5. So that's just something to keep in mind when we factorize. So we get a square minus 2a plus 2 into a square plus 2a plus 2. But because a is divisible by 5, this
P must
term
be
mod 5,
1 mod 4.
sorry?
P must P must be 1 mod 4.
Sure, but we already got a contradiction actually, because if a is 0 mod 5, then this term is 2 mod 5.
Okay.
But if all the prime factors are of the form plus minus 1 mod 5, how on earth did you manage to get a 2 mod 5?
Yes.
Yeah, so we're done actually. So, okay, yeah, you did have to use the factorization at some point. I was trying to remember whether it was just a red herring or you actually use it. But yeah, I mean, this worked out a bit too cleanly. But this really brings out. Hmm.
So, okay, I guess I was wrong. No, what I was telling is that here you get a 2, and the second bracket also, when you multiply it out, you get a 2. So that together gives a minus 1 of 5. So I was just
Wait, minus 1 is okay though. Like we have plus minus 1 is okay. The 2 is the problem. You can never get to 2.
no, like 2, and the next bracket also gives a 2, so you will get a minus 1. So like why is 2 a problem?
Ah, okay. But yeah, that's the point, right? But, I mean, you can ignore the second bracket. You can just say this divides 5 to the k minus 1. And that
Okay.
itself would be a contradiction. Because supposedly all factors here should be plus minus 1. Assuming that a is 0 mod 5, which we got from the full factorization. Okay. Let's take another
so we just
problem.
have to like notice that a to the power 4 is congruent to 0 and 1, and then the previous question.
Yeah. Yeah. So I think the main idea is that, yeah, there are two reasons why you want to use QRs, not just the quadratic case, but also this 5 to the k minus 1. This is something that actually even I never really thought about too much earlier. But now that I think about it, yeah, I've probably used QR more in this form than in the quadratic equations kind of situations. So it is
Also,
something that.
like when do you like prove that A is even? Which case will you
That's a
prove like?
good point. We have missed something, haven't we? Um, hmm. Did we do something wrong?
No, like it wanted us to show that either of those is odd. So we showed that if one is even.
No. Like apparently there should be some solution when k is odd but a is even, right?
I think we managed this.
Maybe it's just the
Yeah,
k equal 1 case. No, wait, what? Yeah, wait, what happens when k is 1? Then a equal 0, for example, works. No, a is positive integer. Okay, but k equal like 3 and No, wait, what? I don't know. Yeah, actually, what is going on here? Did we miss something? I don't think we missed something. I think this is just stronger. Wait, I'm just thinking. Yeah, I think we're okay. If someone notices that there was some sort of problem, then let me know. But I doubt that's the case.
I think we proved that K is always even.
We proved that K is odd when A is.
No, I think we proved that K is always even.
Yeah, exactly. If K is odd, we just proved a contradiction in general. Yeah, I think this is slightly.
You repeat the last part once. I still did not get it.
No problem. So we got that 5 is a QR mod any prime factor of this thingy. Does that make sense?
Like
Like,
5 is congruent to that one. Yeah, I understood until that part. Like,
yeah, so P is plus minus 1 mod 5. Um, so if A to the so because we are working mod 5 kind of now, note that A to the 4 plus 4, like A to the 4 is always 0 or 1 by Fermat's theorem. So if A to the 4 was 1 mod 5, then the LHS becomes 0 mod 5. But that shouldn't happen because 5 can't divide the RHS. So A must be 0 mod 5. But then if we use the factorization of A to the 4 plus 4, which is pretty cool, then on putting A equals 0 here, you just get 2 in this bracket, 2 mod 5. But that can't happen if all your prime factors were just 1 or minus 1. Because 1 into minus 1 into minus 1, etc. can only lead to 1 or minus 1, can't lead to a 2 mod
Okay,
5.
so this thing that either A or K is even was just for confusion.
Apparently, yeah, that is true. I'll just
I'm still
um
confused.
I
It's
guess
like P
P.
divide this thing, like P divides and P is not equal to this. Like how will it matter if it does have like if it is 2 mod 5, 3 mod 5, it can't.
So 1 second. What we proved is that any factor of A to the 4 plus 4 has to be plus minus 1 mod 5. Is that acceptable? Because if there is a prime factor which is 2 mod 5, then that divides this. But that's false because any prime factor of this has to be plus minus 1 mod 5.
Okay, my bad. Okay, got it.
Yeah. So any prime factor of A to the 4 plus 4 is this, but that's false because we found something which should be 2 mod 5 or minus 2 mod 5. Okay. I'll just
Didn't
give.
we use K's odd to get 5 as a quadratic residue?
Yeah. We used K is odd for sure. The question we were confused about is whether A needs to be odd or something.
Okay.
Like that's what we apparently didn't use anywhere. Yeah, I don't think we need to use it. Yeah. It's just there. Okay. Let's do one last. Oh, I think time is close to up. So maybe we'll not do one last problem. But instead, if anyone has any questions about anything, feel
What
free
was
to
the
ask.
source of this?
Source of this, no idea. This was from some class taken by Siddharth Suresh, who is a QR's god, in Sophie about 1.5 years back. So yeah, yeah, that was a really good class. We were really trying to get Siddharth to take this class, but he was busy, sadly. Um, Uh, yeah, there's some other cool things on QR, some of which are on the more theoretical side. So, for example, there is this cool theorem which states that if a number is a QR mod all but finitely many primes, then it has to be a square. So these are some cool things that also turn out to be there. And then there are also things like, you can count the number of solutions to some equations, like for example, you can do something like, uh, I think something like this. You can sum over n equal 0 to, no, wait, I don't really remember the exact thing. But there's some nice things. I think Modern Olympiad Number Theory is also a very good book for QRs. Like you could read the chapter and yeah, there's some pretty cool problems there. Yeah, I think the main thing in terms of Olympiads is just remembering when you can complete squares, remembering when things are odd and you can multiply by an extra factor, and remembering to use quadratic reciprocity because yeah, that's a very powerful theorem. And notice that that's the only thing today we didn't prove because it does not have a very, I mean, the proof is also not impossible, but yeah, I mean, it's not for today. Um, yeah. So also one thing worth noting is that a lot of people end up misusing this quadratic reciprocity just because you mess up the sign or something like that. So if you want some practice, just try doing something like 23 by 47 or something like that because that gives good practice because 23 by 47 actually turns out to be very easy because you multiply it by 47 by 23 and this thing is just equal to 1 by 23 and that's equal to 1. So, just try some things like this on your own until you get the hang of how you want to manipulate these things. And yeah, the general idea is usually you will have a p in the denominator and a fixed constant in the numerator. And quadratic reciprocity will allow you to bring this random p to the numerator and the constant to your denominator, which gives you a relation on what p is mod c, which is pretty cool. And that's what we did in like every problem, by the way. Like here, 3 by minus 3 by p, and then 5 by p, like etc. Okay. Yeah, I think that's mostly it. I'll stop sharing.
So we can like just use it directly without proof or
Yeah,
just
quadratic reciprocity is quotable. Yeah, just say that it's quadratic reciprocity and say the statement if you feel like. I'll stop recording.